For equilibrium, we're going to start with the Le Chatelier question. So, our question is, which way will the following reaction shift if it starts at equilibrium before the changes described below? So we have nitrogen plus 3 hydrogen gas is in equilibrium with 2 ammonia gas, and we have a delta H of reaction of negative 96.0 kilojoules per mole. So let's start with our first step, our addition of nitrogen gas. If we add nitrogen gas, we're adding a reactant. Remember, Le Chatelier's is we're going to try to remove stresses and reverse them. So when we're adding a reactant, that means we want to basically try to do the opposite of that. We want to take away reactants to counter that. So as we add nitrogen gas, the reaction is going to shift towards the right. You can also say that it would shift towards products. Both of these are right. So it's shifting to the right or towards products because we added nitrogen gas. In the opposite way, if we remove hydrogen gas, we're now removing a reactant. So the reaction is going to shift towards the left to try to produce more reactants, to undo that stress and to get back to equilibrium. So we removed reactants. That means we're going to shift to the left. Or we can say we're going to shift towards reactants. This time in C, instead of adding something on the reactant side, we're going to add it on the product side. So we're adding ammonia, and so we're adding something in the product. So to undo that, we're going to again shift our reaction to the left, or towards reactants. Now you've got two more. We have that the reaction mixture is heated. So in this case, we want to think about how this delta H matters. So one thing you can do is you can actually write out the heat portion of this as part of your equation to help you think about it. So in this case, we have negative 96 kilojoules per mole. That means we have an exothermic reaction. That means that heat is going to be given off by the reaction when we do it. So I'm going to write it like this. N squared gas plus 3H squared, not squared, 2 subscript. Nitrogen, hydrogen gas are in equilibrium with, we still have our ammonia, but now we also have heat because heat is being given off. It's like a product. You wouldn't write this in the balanced chemical equation, but for thinking out Le Chatelier, this is a good way to put it. If it were a positive value, that would mean it was going into the reaction, so we're absorbing it, so then it would be a reactant. So, negative enthalpy, product, positive enthalpy, reactant. And now, when we heat it, remember that heating the mixture could also be said with words like raising the temperature. Is like we're increasing this part over here. So that's our stress. So anytime we have a stress, we want to try to undo it. So to undo that stress, we're going to shift towards the left side. Going that way is going to try to remove some of the heat in this and reestablish equilibrium. So this is also going to go left. Now finally, the volume of the container is increased. Remember that if volume goes up, back from our PV equals nRT in 1211, that means pressure is going to go down. So we want to try to undo this decrease in pressure. And so to do that, we do that by adjusting how many moles are present. So if we want to increase pressure, we want to increase moles. Because remember, they are directly proportional, unlike volume pressure, which are inversely proportional. So we want to increase the number of moles of gas we have available to increase the pressure. So in this case, we have 2 moles on the right side, 4 moles on the left side. So when we increase pressure, we're going to shift towards the reactant side again. So this is going to shift us left. Remember that if we had the same number of moles of gas on each side, like it was 2 on the left and 2 on the right, then you wouldn't be able to shift it with Le Chatelier like that because it just wouldn't make any adjustments to your reaction. It wouldn't help. Also, some things are going to not change. Like you could have had a solid here, and then it would be a heterogeneous type reaction, equilibria, and so the solid wouldn't take part of your equilibrium constant, so adding it wouldn't change anything. Similarly, a catalyst, like we had in kinetics, is not going to actually change your equilibrium. It's only going to change the rate at which you get there, but the equilibrium state itself, even if it takes way longer, is still going to be the same when we have a catalyst present. So we wouldn't treat that like that was going to change anything. So that really covers most of the examples you can have with different ways Le Chatelier can move a reaction around. So now let's do some problems with equilibrium constants. So what is the equilibrium constant, in this case Kp, for the following reaction based on the provided partial pressures if they were taken at equilibrium? So this reaction, we have these pressures. So the main thing here is just to come up with what our equilibrium constant looks like. So Kp, and remember if it's Kp, that means we're going to use pressures. And if it's Kc, we're going to use concentrations, which are going to be in molar. And these pressures are going to be in atmospheres. So we have pressure of reactants, so we have SO2 times Cl2, all divided by pressure of reactants, SO2, Cl2. And remember, if there had been coefficients in front of these, they would go as exponents. So if you had 2 SO2, this would have been P SO2 squared. But since none of them have coefficients, we just have 1s on everything. And now make sure before you put these in that these are all in atmospheres, but then we don't have to worry about it after that fact. We don't write a unit for the equilibrium constant at the end, but it's understood because it's Kp, everything that was part of the equilibrium constant was in atmospheres. So we have 0.357 times 0.584. Yeah, so if you leave it in torr, you won't get it right. Or wait, depending, but yeah. 7.16 times 10 to the minus 5. So these are our three values. There's no squares or anything. So if you multiply the top together and then divide by this number at the bottom, you should get that your Kp, equilibrium constant, is 2.91 times 10 to the third. And that would be Kp for this reaction, given that it is already in equilibrium. So if we want you to find the equilibrium constant, we have to give you some conditions that let you find all the equilibrium concentrations. So you'll have to find equilibrium concentrations before you can get it towards the actual this. So you wouldn't be able to do this if you had just non-equilibrium conditions. You have to be given some information to be able to find equilibrium conditions. Even if we don't give you every single one that way, we'll give you enough information to find it. That's one of the things we did in class. So now let's look at let's look at this one, where we're going to actually have to do, this one we're going to find, let's see, which direction the reaction is going to do. So this is where we're going to look for at Q, our reaction coefficient. So remember, Q, we're going to compare to K to figure out where the reaction is. Are there more reactants than we expect? Are there more products than we expect? Or are we already in equilibrium? So to start, since we're using Kc, that means we need concentrations. And you weren't given concentrations directly, but you're given information to find them because you have the volume of the container and the moles of gas. So that means we can go with the concentration of NO2 is going to be equal to the 0.044 moles that we have, divided by the volume of the container, which is 1.75 liters. And for that, we're going to get the concentration is 2.51 times 10 to the minus 2 molar. We're then also going to have our concentration of N2O4. That's N2O4, not 2N40. It's going to be equal to, we have, let's see, 0.076 moles. And again, we still have a 1.75 liter container. And when we do that, we're going to get 4.34 times 10 to the minus 2 molar. Now, we need to find what Q is. So remember, Q is found the same way as K. It's just that it's at a set of conditions that might not be equilibrium. So this is going to be N2O4 over NO2, and the NO2 is squared because we have a 2 coefficient there. So we're going to plug our numbers in, and we have 4.34 times 10 to the minus 2 all over 2.51 times 10 to the minus 2, and that's going to be squared. We plug all this in. Let's see, 4.34 10 to the negative 2 divided by 2.51 to the negative 2 squared. Almost forgot my square. And then we plug this in, and we're going to get a value of 68.9. So we want to compare Q to K. So we have 68.9, and then 1.69 times 10 to the second is just a way of saying 169. And that means that this is going to be less than this. So Q is less than K. And if Q is less than K, the reaction will shift towards products. Remember, the products are in the numerator. So as the numerator gets bigger, your number is going to get larger. So if we want to get 68.9 to get to 169, the numerator has to go up and the denominator has to go down. Because remember, one can't change without the other because of how equilibrium works, unless we add something. But we're not going to be able to shift it other than changing both. So we're going to make the numerator go up, denominator go down. If this number had been larger than 169, this would be the other way. You would want the denominator to go up because that makes the number smaller. So this is what's going to happen. And if you were asked to just find Q, it would be this. And maybe you're just asked, is Q less than, greater than, or equal to K? That would be this. So just pay attention to what the question's asking to make sure you know how to answer it. So now we have two equilibrium problems we're going to do. One that will allow us to ignore X, and one that won't. So here, we have an equilibrium condition. We're told we start with 1 molar of this material, and that we want to know how much one of the other things on the other side, what its concentration is. So for this is a good hint that you want to use an ice table. If you're given a starting condition, and we know we want to find the final condition, and we're given an equilibrium constant. You will do a lot of these in the next exam, and I'm talking exam 3, like we have 2 chapters of this. But for this chapter, the main way to know is, hey, you have a concentration, you want to know a final concentration, and you've given me the equilibrium constant. So I have those things, I can use an ice table. So initially, I have 1.00 molar of this. For now, we're going to say we have 0 of this. For any of you that have taken the course before, or if you're watching this video as a review later, note that this is actually approximately 0, but we're going to cover that in next chapter. So for right now, we're just going to say 0. It'll be fine for this. And then we're going to put the 0 here for our ion. So our change, since we only have reactants, they've got to go away. We can't make more reactants with no products. So this is minus x, this is plus x, this is plus x. We plug our numbers in, 1.00 minus x, x, and x. Then we're going to set up our equilibrium constant. It's going to be equal to, we've got our products on top, and they're both aqueous, so they're both going to show up, our H plus, C2H3O2 minus, and then we're going to have it all over our HC2H3O2. So now, we've got that. We're going to plug our values in from our ice table. So we have x times x, which gives us x squared. So this was x, that was x. We multiplied those together, got x squared. Divide that by, we have 1.00 minus x, but we said we could ignore x, we think. The reason I'm doing this is I'm looking at my k, and my k is fairly small. I like being about smaller than 10 to the minus 3 or so is where this will work a lot of the times. And once I see that, I go, okay, there's a very good chance that x is very, very tiny. The specific rule you're looking for is x needs to be within no more than 5% of your starting concentrations. So in this case, it needs to be smaller than 0.05. So in this case, it's very likely that because of how small Kc is. So I'm going to solve my problem while ignoring x. And then at the end, I can check. And if I'm wrong, I need to go back and resolve it with the quadratic formula. I will do my best on your exam to make it very obvious when you can. Your Kc will be very small in cases where we're going to be able to ignore x. And that'll make this math a lot faster. Because we don't do a quadratic equation, this should be pretty easy to solve. We then solve in the value for Kc, which is 1.8 times 10 to the minus 5th. That came from right here. We just plugged it in for Kc. Now we see the 1, when you divide by 1, nothing happens. So we just have x squared equals 1.8 times 10 to the minus 5. We take the square root of both sides, and that's going to give us that x is equal to 4.24 times 10 to the minus 3. A lot faster than doing a quadratic. And we can check, and this number is very clearly smaller than 5% of 1. 5% of 1 would be 0.05, which is going to be 5 times 10 to the minus 2nd. So we're good. And the problem specifically asked for this ion's concentration. So we're just going to answer that one. Is going to be equal to 4.24 times 10 to the minus 3 molar. Note, this does not always have to be the same thing as x. Remember, you have to check here. I got that from here, our equilibrium number. This could have had a 2 in front of it, then I had to multiply by 2. I could have had some starting amount here, and then I would have to add this to it, or subtract it if it's a negative, because we're actually going towards reactants. So make sure you check that. And remember, sometimes it will be that your products go towards your reactants. It doesn't always have to be reactants towards products. You will have more that are set up like this, but that is not a requirement necessarily. So let's look at one more example. This one, we're not going to be able to ignore x. It's going to be a bit more work because of that. So here, we again have starting conditions, and we've got equilibrium constant. We're asked for our equilibrium concentrations. In this case, all of them. That's a good hint. I want to use an ice table. Starting conditions, equilibrium constant. What do you get at equilibrium? Really good way to do that. So those are the keywords I'm looking for. So we have I, C, E. And again, this time we've got molarities. You can also have pressures. You'll do all the things the same way. The way you know that is if you have Kp, you would be using pressures. Note, if I had given you Kp, you would have to use the Kp to Kc conversion equation to be able to get it into Kc to use it with molarities. So make sure you check that you have the constant that would match up with the data you're using. So here, we're going to go with our starting concentrations are 0.1000, 0.125, and 0. Our change, we only have reactants again, so this has to go away. So minus x, plus x. And then we're going to have 0.10. I'm not worried about putting more zeros. We'll remember there are 4 sig figs in that number, but we're not going to worry about it for now. This number still has 3.125 minus x, and then plus x is all. So now we've got to plug these into our Kc. So Kc is equal to products over reactants. So we've got CoCl2 divided by CO, carbon monoxide, times chlorine gas. So here, when we plug this in, I want to point out, this step here, If you're 100% confident, I'm okay if I don't see that, but know that this is a place that lets me give you partial credit. So if you mess up plugging things in, having this step helps me a lot because I can give you credit because I know you knew how to set this up. So if you can, please remember this. It helps a lot. Also show this next step. Show you plugging the numbers in rather than trying to solve for Casey instantly. This is a type of problem where if you mess up a little bit but don't show any work, it is really hard to give you partial credit because I can't see what you're doing. So we have x over 0.10 minus x, 0.125 minus x. And as you'll be able to tell as I do the math here, there's a lot of places you can make math mistakes. Work is incredibly helpful. I recommend, sometimes I show more steps than I think you should because I want people, on the test, because I want people to be able to see what I'm doing. I recommend on ice tables you show every step I'm about to do because they're every place where you can make a mistake and it means I can give you partial credit. So now we're going to multiply the denominator together. So it's still KC equals x over 0.0125 minus 0.225x plus x squared. So I just did FOIL. And when I did FOIL, I added the two x's together, the two values for x already. You can do them separately if you'd prefer. And now I'm going to go ahead and I'm going to remember that this is going to be equal to 255. So I'm going to put the actual number in. It's not that KC went away, but I'm replacing it with a number. And now we're going to multiply 255 by everything in this denominator. I'm going to do that. When I do that, I'm going to get that 255 x squared minus 57.4x plus 3.1875 is equal to x. We now, to use the quadratic formula, have to move everything over to the left side. So I got to get this x over, so there's a 0 here. So let's make our little divider. So we move that over, and we now have 255 x squared minus 58.4. Nope, you were subtracting the x, and this is negative, so the number gets big. Gets smaller, but the absolute value gets bigger. Plus 3.1875 is equal to 0. We're now going to use our quadratic formula, which is available on your equation sheet if you don't remember it. Negative b plus or minus square root b squared minus 4ac all over 2a. I'm now going to plug my values in. And this is one that I know a bunch of people will skip, but I think it's good to show this step because it is very easy to put this in your calculator wrong. And this lets me know that you know what b, a, and c are. Note, instead of putting them in here, you could also on the side just show me A, B, and C and not have to draw it out like multiple times, but please show me that you know what this is. And we'll have a quick discussion in a second about what something your calculator will make you do wrong sometimes if you're not paying attention. So I'm plugging all these values in, and I did not have enough room on your paper. Please try to have enough room. I can't really make more screen here. All divided by 2 times 255. So yeah, I'm going to plug this in my calculator. What I like doing is I solve everything under this radical first. I then square root it, and then I'm going to do the rest of the problem. So when I do this, I'm going to plug these values in. Note that when you square this negative 58.4, if you're using a graphing calculator, what many people will do is they'll just put in a negative 58.4 and then press the square button. What that does to the calculator, though, is it thinks you want to square 58.4 and then make it negative, which is strange because you think of the negative as belonging to the number, but it doesn't with the way it reads the syntax. If you square a number, it has to be positive. So you need to check that because you will get something wrong. If you do that, you might get the square root of a negative number, which you won't be able to do because that's irrational, or you might still get something that turns out positive but is very wrong. So make sure that you check that when you do that. So we plug all that in. We're then going to take 2 times 255 is going to give us 510 on the bottom. And so we do all of this. We're going to get two values for x. Remember, this is an equation for x. So there are two possible values you get when you plug all this in your calculator. You get 0.139 and 0.0898. If you check back in your original ice table, x cannot be 0.139 because you would get 0.10 minus 0.139 and you would have a negative concentration of carbon monoxide. That means this has to be your x value. So now we're going to plug it into all three because if you end right here, you're not done yet. So we've got to plug 0.0898 into all three of these equations in our ice table. So I'm going to get carbon monoxide is equal to 0.0102 molar. We're going to get that Cl2 is equal to 0.0352 molar. And we're going to get that Cl2 is equal to 0.0898 molar. Again, it's possible to have none of the answers equal exactly x, but you can see that a couple of these concentrations were different than our x value. So make sure you check through that and see What am I supposed to write down? Don't just find X. You're not done yet. And you're really close to done, so you want to get all the credit. If you get to this point, it's only a 1 or 2 point mistake on a multiple choice, but it's still frustrating when it's like, oh my gosh, you're so close. You got all of it. So try to make sure you get that last part. So with that, I hope you do well on your exam, and I will see you in class.